Have you ever really stopped to think about what holds our world together? I mean, everything from the water you drink to the air you breathe, it all comes down to chemical bonds. You can think of them as these invisible architectural plans that dictate the shape, the strength, and really the substance of everything around us. So today, we're going to map out one of the most powerful blueprints for understanding this architecture, valence bond theory.
Okay, let's just dive right into a puzzle. You know those simple Lewis structures we all learn? A single line means a single bond. So you'd think the bond in a hydrogen molecule and a fluorine molecule would be kind of similar, right? But check out the numbers. It takes a whopping 435.8 kilojoules per mole to rip apart that HH bond, but only 155 for the FF bond. That's a huge difference. That simple line just can't explain why one is so much stronger than the other. This is what we call the enthalpy paradox, and it's a huge clue that we need a much deeper theory.
And that's really the thing. Our older models just had their limits. I mean, the Lewis approach is great for a basic sketch, but it tells you nothing about energy or the real 3D shape. Then you have the SEPR theory. It's pretty good at predicting geometry, sure, but it's more like a set of rules. It doesn't explain why molecules take those shapes. And that brings us to the hero of our story today, valence bond theory. When it came on the scene back in 1927, it promised to finally connect the dots between atomic orbitals and electron configurations to explain how a bond actually physically forms. So to really get a handle on this, here's our game plan. We're going to start with the basic physics of forces and energy. Then we'll uncover the quantum secret at the heart of it all, orbital overlap. From there, we'll see how to build molecules with two types of connections, sigma and pi bonds. And then, and this is the fun part, we'll see where the theory hits a fascinating wall with the methane molecule, which is going to point us to what comes next. All right, let's start with the absolute fundamentals. Before we get into any of the quantum weirdness, you have to remember that a chemical bond is, at its core, a story of pushes and pulls. It's all about classical forces finding a perfect balance. This image here shows it perfectly. It really is a tug of war. As two atoms get closer, you've got these attractive forces pulling them together. You know, the positive nucleus of one atom is pulling on the negative electrons of the other one. But at the very same time, you've got repulsive forces trying to shove them apart. The two positive nuclei are pushing on each other, and so are the two electron clouds. A stable bond only forms if that net attraction wins the tug of war. And if we map those forces out as energy, we get this amazing graph. When the atoms are really far apart, nothing's happening. As they get closer, attraction takes over, and the energy of the whole system just plummets. But if you push them too close, repulsion kicks in hard, and the energy shoots through the roof. And right there, at the very bottom of that valley, that's the sweet spot, the Goldilocks zone. It's the point of minimum energy. For a hydrogen molecule, that happens at exactly 74 picometers apart, and it releases 435.8 kilojoules per mole of energy. That right there, that's the bond's length and its strength. So that energy diagram is a great start, but to get the real story, we have to go deeper. We have to dive into the quantum world. And this is where valence bond theory really starts to shine. So here it is, the central idea of VBT. A covalent bond is formed by the physical, spatial overlap of atomic orbitals from the outer shells of two atoms. Think of them as actually merging into each other. Now, there are a couple of key rules. One, the electrons in those overlapping orbitals have to pair up with opposite spins. And two, the amount of overlap is directly tied to the strength of the bond. The more those orbitals can overlap in space, the stronger the bond is going to be. It's really that simple, and it's incredibly powerful. Okay, now hold on. Before we go any further, we have to clear something up because it trips everybody up. When you see diagrams of orbitals with plus and minus signs on them, it is so important to remember these are not electrical charges. They have nothing to do with positive or negative charge. They represent the mathematical phase of the electron's wave function. The best way to think about it is like a wave on a pond. The plus sign is like the peak of the wave, the part that's above the surface, and the minus sign is like the trough, the part that dips below. It's just a way to describe the wave's amplitude at that spot, and this phase is what determines everything about how two orbitals are going to interact. Which leads us to the rules of engagement. When two orbitals meet, there are basically three things that can happen. First, you get positive overlap. This is when two lobes with the same sign, say plus and plus, meet up. They reinforce each other, that's called constructive interference, and boom, you get a bond. Second, you can get negative overlap. This happens when opposite signs meet. They cancel each other out, creating a dead zone with no electron density and no bond forms. And finally, you can have zero overlap if the orbitals are just oriented wrong and don't really interact at all.
Okay, so now that we have the rules, we can actually start to see how atoms build molecules. They use two main types of connections, kind of like how a builder would use different types of joints to build a house. And this slide shows the two fundamental types perfectly. On the left, you have the sigma bond. Think of this like a direct, head-on handshake, right along the line connecting the two atoms. This is the strongest, most basic kind of covalent bond. Then on the right, you see the pi bond. This is more of a sideways overlap between two parallel p orbitals. It creates these pockets of electron density above and below the main bond axis. This table breaks down the differences really well. Sigma bonds have that big head-on overlap, so they're stronger. Pi bonds have that weaker sideways overlap, so they're not as strong. But the real takeaway, the most important part, is right there in that last row. A sigma bond can exist all by itself. It is a single bond. But a pi bond can never exist alone. It's always an add-on to an existing sigma bond, and that's how you get double and treble bonds. So far, so good, right? Valence bond theory seems to be working great. It explains why some bonds are stronger than others and gives us a clear mechanism. But now we're going to throw it a curveball. We're going to test it with a super common molecule, and a huge puzzle is about to pop up. Let's think about methane, CH4. If you look at a carbon atom in its normal, ground state, it only has two unpaired electrons. So based on everything we've said, it should only be able to form two bonds. But we all know methane has four bonds, so what gives? Well, the first step is that the carbon atom gets a little jolt of energy and gets excited, which bumps one of its 2s electrons up into an empty 2p orbital. Now the carbon has four unpaired electrons, all ready to form the four bonds we need for methane. But this is exactly where simple VBT slams into a brick wall. That excited carbon atom has three p orbitals, and they're all oriented at 90 degrees to each other. So if we just overlap those with hydrogen atoms, our theory would predict that three of the CH bonds should be at 90-degree angles, and the fourth bond would just be somewhere else. But the reality? We know from countless experiments that methane is a perfect, beautiful tetrahedron. Every single HCH bond angle is exactly 109.5 degrees. Our theory just predicted the wrong shape. Now, this contradiction doesn't mean we should just throw valence bond theory in the trash. Not at all. It just means it's incomplete. It's a fantastic first step, but it needs an upgrade to handle the full three-dimensional complexity of the real world. So here's where we stand. Simple atomic orbital overlap is brilliant at explaining the mechanism of bonding, the why and the how of it all. It gives us a solid reason for bond energies and bond strengths, but as we just saw plain as day with methane, it just can't predict the actual beautiful 3D shapes that molecules take. The geometry is a mystery. And this quote just nails it. The theory, as we've discussed it, is incredibly powerful, but it has a clear boundary. To get past that boundary and start explaining the precise, amazing shapes of molecules in 3D space, we're going to need one more piece to the puzzle. Which leaves us with one last, really fascinating question. If just mashing together pure s and p orbitals doesn't give us the right shapes, what does nature actually do? How do atoms mix and match their orbitals to create these perfect geometric arrangements that build everything from methane all the way up to DNA? Well, the answer lies in the next revolutionary idea, the hybridization of atomic orbitals. But that is a story for our next explainer.